Good day, everyone. I'm Emilia. Today, I'm representing our group, which is Group 2, to present Mechanical Engineering's Laboratory 1, General Machining, which focuses on milling process. So, this is our group members, which are Emilia, Chong Hui Wen, Chair, and Wong Haojia. So milling is a machining process where a rotating cutting tool removes unwanted material from a stationary workpiece. It's commonly used in manufacturing because it can produce parts with high accuracy and good surface finish. Common milling operations include fast milling, slot milling, drilling, boring, and tapping. The objective of this lab is to help us understand the milling process, process planning, machining calculations, and material removal rate. So this slide shows the analysis of our workpiece. The dimensions of the workpiece are 50 millimeters in length, 46 millimeters in wide, and 22 millimeters in height. Based on the engineering drawing, several machining features were required. These include fast milling, a 40 by 8 millimeter slot, a diameter 8 through hole, and M8 counterbore, and a 4 millimeter step. Also, the brings to remove sharp edges. These are the tools and equipment used during the experiments. The main machines used were the vertical milling machines. We use of machines vines to securely hold the workpiece during machinings. The cutting tools include end mill cutter, fast mill cutter, twice drill set, central drill, and counterbore tool. For measurement, we use a vernier calipers. So each tooth has a specific function. The vertical milling machines perform the machining operations. The machine winds prevents movement and vibrations of the workpiece. The end mill cutter is used for slot and step milling. The fast mill cutter creates smooth, flat surface. The twice drill and central drills are used to produce accurate holes. The counterbore tooth enlarges the upper part of a hole so the board head can fit properly. Lastly, the vernier caliper is used to measure dimensions accurately. That's all for the introductions and preparation sections. Thank you.
Hi, my name is Jo. Now I will talk about process plan. Before machine begin, a process plan must be prepared. The purpose is to determine the correct sequence of operation to ensure accuracy and efficiency. For this workpiece, the process starts with face milling followed by slot milling, drilling, counterboring, and finally deburring and inspection. Machine setup is a critical step because it directly affects machining quality. The workpiece was clamped securely using a machine vise. After established the datum reference, the cutting tools are installed and machining parameters are adjusted before starting the operation. The machining process follows a specific sequence. Face milling is performed first to create a flat reference surface. Slot milling is then carried out, followed by drilling and counterboring operation. Finally, the boring and inspection are conducted to ensure the workpiece meet the required specification. This flowchart summarizes the complete manufacturing process from raw material preparation until the final inspection. It shows the logical sequence of machining operation required to produce the finished workpiece. That's all from my part. Now we'll pass to my group mate.
Hi, it's me, MA25053, Cik Nur Syahrir binti Cik Sulaiman. So I will present my part, which is machining time calculation for slab milling and face milling and material removal rate. So first we go to the spindle rotational speed. For spindle rotational speed, we use V divided by pi and multiply by D. V required to cutting speed and D required to diameter of workpiece. So next we have feed rate. Feed rate is n, which is spindle rotational speed, multiplied by n, number of discs, and multiplied by f. So we can get our feed rate. So machining time required for slab milling. This is the formula. So L required to length of cut, and required to a push distance, and F required to feed rate. So where A we can find by use this formula for slab milling only. A is the push distance required to fully engage the cutter. So next we go to the face milling. So for face milling, we have two conditions to find A, which is condition one is the cutter is centered over the workpiece. So this is the formula for A, and for condition two, the cutter is offset to one side. So this is the formula for A. So where O is a over travel distance and W is a width of cut. So for formula for machining time required for face milling, it seems like slab milling, just add 2 in front of A. So next we go to the material removal rate. Material removal rate, W multiplied by D and multiplied by F. So W is a workpiece width, and D depth of cut, and F is a feed rate. So that's all for me.
Hi, my name is Wong Hao Jia, and today I will present what are the safety precautions that we have to follow before doing this lab. So, first and foremost, we have to wear our safety glasses, shoe, and lab coat. For girls, they have to tie back their long hair and remove loose clothing or jewelry. Next, we have to verify the machine and tool condition. Remove chuck keys and adjustment tools before starting. Moving on, securely clamp the workpiece in a vise or fixture before activating the machine. Moving on, we also have to keep our we also have to keep our hands away from the rotating cutters. We have to use a brush and never use our hand to kill the metal chip. And moving on, we have to turn off the machine and wait for the spindle to fully stop before measuring or adjusting. Last but not least, we have to operate only under instructor supervision and maintain a clean clutter-free workspace. And this is the procedure of doing the lab. First, we have to wear our personal protective equipment, prepare the tools, and review the engineering drawings for specs. Next, we have to determine the machine sequence, tool selection, and cutting parameters. Moving on, we have to secure the workpiece, align the cutting tool, and set the speed or feed rate. Moving on, we have to machine the part according to plan while verifying the dimension mid-process. And after processing, we have to debug and inspect the final product, then clean the machine and the workspace. So for the discussion of the lab, one of the main strengths is it managed to bridges the theory, and we get to experience by doing the milling hands-on. Next, it also built core competency in machine setup, tool selection, and precision measurement. And it also managed to raise the safety awareness and deepen the understanding of manufacturing workflows. For the weakness of this lab, it is very time intensive as high precision steps demand meticulous attention. So it did slow down our execution time. And this lab has a low error tolerance. If any misconfiguration, if there's any misconfiguration, it will cause the workpiece damage, and it will lead to waste materials, and we have to rework the lab. And also human error, some dimension were slightly off because of uneven manual feeding or small mistake reading the vernier caliper. So to conclude, this lab experiment for the core objective, we managed to successfully execute the fundamental of milling operations and observe the material removal via rotating cutters. And for technical insight, we mastered how speed, feed rate, and depth of cut directly impact surface quality and dimensional accuracy. And for the precision and setup, we learned that meticulous tool alignment and workpiece setup are critical to avoiding measurement errors. And raised the it also encouraged the safety culture by reinforced the necessity of personal protective equipment, secure work holding, and staying clear of moving parts. And last but not least, it enhanced our teamwork, group communication, and collaborative data documentation during machine operation. That's all from our group. Thank you.